And my today's topic is linear graph or graph theory. And since time is very limited, so I'm going to move a little bit faster. But I hope that you understand the core of these topics which are there in the graph theory. But I shall not go line by line with the notes that I have already shared with you a long time ago. I hope that you have gone through first three chapters as I asked you to do so. So I will briefly cover all these topics one after another, and you just pay attention to what I say. First of all, graph is kind of a structure which is it is also an algebraic structure which actually has four different things in it. One thing is that it is containing a vertex set V. It contains an edge set E. It also contains a function phi. It also contains a function psi. But as you can see in the book, they have not mentioned about the function. Okay, so in different books, different authors actually try to represent graph in a different way. Let me tell you what are the meanings of all these things, and especially what are the meanings of this phi and psi. So or in some books you can also get the expression as VE and only phi. In some books it is either triplet, or in other book it is also written as a quadruplet, and here it is written as a pair. So they have emphasized only on the vertex set and on the edge set. So V is the set of vertices which are present in the graph, and E is the set of edges. Okay, because you see, suppose if I consider a vertex containing 2 points only, V1 and V2, and if I take the set capital E to be a singleton set, then it implies that this V1 and V2, these two vertices are connected by the edge E. Okay, so this particular structure that I have drawn over here, this structure is called a graph, which we can denote by capital G. Or you can take the vertex set capital V to be containing only 1 point, small v, and your edge set you can take to be the null set. Okay, so in that case, you will again get a graph which contains only the point V and no edge is there. So you can give the name of this particular graph to be G1. Okay, and sometimes this type of graphs are also called null graphs, where edge is not present. It is also called null graphs. And this particular vertex which I have drawn over here for this graph G1 is called the isolated vertex. But you cannot consider a graph G2 where if you are taking the vertex set to be null set and edge set to be containing an element, say E, because this is not actually possible. Is not possible. Why it is not possible? It is because if I draw an edge E, this particular edge is always containing two end vertices. So if even if I don't want to the vertices in the graph, the vertices automatically, the pair of vertices automatically come. So the first vertex is called the vertex 1 and the second vertex is called the vertex 2. Without drawing the vertex, you cannot draw the edge. So edge is always associated with two vertices, and therefore this type of graph is not possible. So in a graph, the vertex set can never be an empty set. Okay, so here you can consider the vertex, you can consider the graph to be an ordered pair V and E. Here you can consider the graph G1 to be the ordered pair. You can name it as V prime and E prime. So this G and G1, these are two different graphs. G2 is not at all a graph. But what about this phi and psi that I'm talking about? Phi is a function. Phi is a function from the vertex set, vertex set V2 or V cross V to an edge set capital E. It is a function. It gives a connection between the Cartesian product of the vertex set with itself to an edge set. So suppose I am considering the two elements V1 and V2 from the vertex set V cross V, and if I apply the function on the pair V1, V2, you will get an image as, say, small e. That means mathematically it implies that these two vertices are connected by the edge small e. Similarly, psi can be defined with respect to the connection of edge to the vertices. Okay, so we shall not go with this particular, we shall not try to contain in the algebraic structure this function psi. This will be more meaningful if I consist of only, if I consider only one function phi, which takes two elements from the Cartesian product of the vertex set with itself, and it relates the pair to a particular edge. Okay, so it is far better to consider this triplet rather than this ordered pair, because in graph theory, how the vertex, how the edges and vertices are related to one another, that particular thing is also very important. So this is all about the definition of graph. Now here, as you can see below, a graph is given, and also in this particular graph, let me scroll down, you will be able to see it. In this particular graph, you can see that some special type of edges are mentioned. If you consider the vertex V1 and V3, you will see that the vertex V1 and V3 are connected by two edges. One edge is E4 and another edge is E5. And this vertex has got one extra edge, which is E1, which connects the vertex with itself. So such a structure where two vertices are connected by more than one edge is called, this type of structure is actually called parallel edges. And the structure where a particular vertex is joined to itself by an edge like this is called self loop. Okay, so in this particular graph, you can see that these parallel edges are present. E4 and D5 are parallel edges, and E1 is a self loop which connects the vertex V2 to itself. Also, this type of vertex which is the end point of only one edge, this type of vertex is called the pendant vertex. V1 is not a pendant vertex because V1 is the end vertex of three different edges. If I consider the edge E3, if I consider the edge E4, and if I consider the edge E5, in all these cases, V1 is the end vertex. V3 is similarly the end vertex of the edges E5, E4, E6 respectively. So these are not pendant vertices. Pendant vertex is that vertex which is the end vertex of only one edge. So here the pendant vertex is V5. Now imagine that I'm going to remove all these edges from this particular structure. If I remove all these edges from this particular structure, you are left with only the vertices V1, V2, V4, V3, and V5. All these vertices will be present and you are removing the edges. Then this is kind of a graph which will be containing 5 isolated vertices. And but you can never remove the vertex by retaining the edge. This cannot be done in this particular case. And there is a special graph which says that, say for example, if I consider this triangle, for instance, this is one of many examples. I'm considering this triangle V1, V2, and V3. And these three edges are considered, E1, E2, E3. This triangle has no parallel edge and no self loop. Okay, so any graph which has no parallel edge or self loop, such a graph is called a simple graph. Such a graph is called simple graph. So simple graph, the structure simple graph is actually very important, and they play a very fundamental role in the study of graph theory. Okay, so a graph which is having no parallel edge and self loop is called the simple graph. Now let's move on. I think in the next page, the definition of simple graph is given, and it has to be. See, here the definition of simple graph is given. A graph that has neither self loops nor parallel edge is called a simple graph. Otherwise, if in the graph the self loops and parallel edges are present, such a graph is called a general graph. Okay, so so I'm skipping these definitions and these examples. You have the book with you. You can go through these examples very well. One important point that I like to mention corresponding to the graph, as you can see in the figure 1.3, is that in this particular graph, 4 vertices are present. The vertices have not been named, but you can very well name those vertices, okay, in a counterclockwise or a clockwise manner. But the names of the edges have been mentioned. What is important to this particular graph is that, as you can see, these 4 corner vertices have been made bold, because these corner points are actually the vertices of the graph. But here, as you can, it seems as if this particular line, that is the edge E, and this particular line, that is the edge F, they are intersecting at a point, this point which has not been named over here. But this is not a vertex. Actually, the figure is not like this, as you can see it over here, because you are actually, at the end of the day, you are actually seeing the two-dimensional figure. If I want to draw this particular figure, then it correctly must be drawn in the following manner. So if I join this vertex and that vertex together, suppose I'm naming this vertex as V1 and this vertex as V2, and this vertex I'm naming as V3 and this as V4. If I want to join V3 and V4, then it is actually where it goes above this another vertex. So there is a kind of, actually it is this particular edge E is lying on a plane, and this particular edge F is lying on a different plane. So it is not actually intersecting at this particular point, and therefore this vertex, this intersection point, has not been made bold, because it is not at all a vertex. So this you have to keep in mind. Okay, so let's proceed. Now, I have seen often that whenever a teacher goes to the classroom, he often discusses the Königsberg bridge problem, and nowadays it is so famous with all of us that we know at least what Königsberg bridge problem is. So I'm not going to describe the problem to you. You can read it from this particular book. I am quickly moving on to the problems, because actually time is short and I have to discuss the problems. So I'm skipping these examples, and I'm going to my next definition, which is actually very important for studying graph theory. It is about incidence and degree. To know a particular graph, it is very important to know about the degree of the vertices. And degree of the vertices is kind of a thing which tells you how many edges are incident upon that degree, or upon that particular vertex. Suppose you have this particular straight line. Let us think with very simple examples. I'm considering 2 examples. This is my graph G1 containing only 1 vertex V, and this is my graph G2 containing 2 vertices V1 and V2. Okay. Now, if I ask you how many edges are incident on V, how many edges are incident in the figure 1, that means on the vertex V, your answer is 0. No vertex is incident upon this particular answer is no. Nothing. Okay. So no edge is incident upon this vertex, and therefore degree of this vertex is equal to 0. Now, if I ask about the degree of this vertex V1, then you see that on this vertex, one edge is incident, that is E. So degree of V1 is equal to 1. And in this vertex, if I ask you about the degree of the vertex V2, on this particular vertex, only one edge is incident, and therefore the degree of V2 is also 1. Okay. Now, suppose let us make the figure a little bit complicated. Let us make the figure a little bit complicated, and I am considering the graph G2, but let us name this graph G2 as G2 prime. And this time what I'm going to do is that I'm going to connect V1 and V2 with another edge. So it is my edge E and this is my edge E prime. And suppose I'm considering another edge E double prime, which is actually the self loop. Okay. So now according to the definition and of the incidence and degree of the vertex, all the mathematicians in the mathematical community have decided that they will consider the degree of the vertex V2 not it seems since on this particular vertex, actually you can see this vertex is connected to 3 different edges. So probably you are thinking that the degree of the vertex will be 3. Why? Because E prime, this particular edge is incident upon V2. E is incident upon V2. So we have already got two edges. Now again, another edge is there, E double prime, which is incident upon V2. So you think that 3 edges are present, but and so the degree of the vertex will be 3, but it is not true. Because mathematical community has come into agreement that they will count the self loop twice. So degree of the vertex will actually be 3 plus 1, that is 4. Why it is so? Because the self loop E double prime will be connected twice, will be counted twice. Sorry, not connected, will be counted twice, and therefore degree of V2 will not be 3, but it will be 4. So this is so what is actually degree of the vertex? Degree of the vertex gives you the how many edges are incident upon this particular vertex. That is called the degree of the vertex. Now let us move on to the next page, and there is one important theorem which is waiting for you. Let us discuss this theorem. First of all, I'm going to discuss 2 theorems which are proved, which has already been proved in the in this particular book, and then I'm going to discuss 2 more results which are there in the exercise. So now you see that if I consider an edge like this edge I am drawing, so automatically it is giving us 2 different vertices, V1 and V2, because I have already told you that without drawing the vertex, you cannot draw the edge. Vertices are always associated with an edge. Now, if I ask you that what is the degree of this vertex V1, you know that this degree of this vertex is 1. And if I ask about the degree of this vertex, this is also 1. Why this value 1 is coming? This value 1 is coming because only one edge is incident upon V1. So this degree is the contribution of this particular edge. And this degree is also a contribution of this particular edge. Here the edge is same. Here the edge is same, but it is contributing 2 different degrees to the 2 different vertices. So if I write it in the following manner, one edge contributes 2 degrees always. As you can see from here, one edge contributes 2 degrees. Now, if I consider that in my graph capital G, if I consider my graph to be capital G, and if I consider that in this graph, small e number of edges are present. So if one edge contributes 2 degrees, e edges contribute twice e degrees. It's a simple unitary method that I have applied over here. And if in this particular graph, there are n vertices, if I name those vertices V1, V2, Vn, then it is quite obvious and it follows from this simple arithmetic that sum of the degrees of all these vertices taken together will be twice the number of edges. Okay, so that has been written in this particular short form. So this is a very well-known formula that the sum of the degrees of all the vertices in a graph is equal to twice the number of edges. Now let us discuss our previous example. Now, if I consider this example, V1 and V2, which is connected by the edge E1, E, then it is, you can see that degree of V1 is equal to 2 and degree of V2 is equal to, sorry, degree of V1 is equal to 1. Degree of V1 equals to 1 and degree of V2 equals to 1. So degree of V1 plus degree of V2 actually gives you 2. And this can be written as 2 into 1, where 1 is the number of edge present in this particular graph. So this satisfies the given theorem. So it is being satisfied. The given theorem is being satisfied. Now, if I consider the other example that I drew, that I considered with self edge and self loop and parallel edge, let's see what happens over there. So if I consider the example once again, so suppose I'm taking, just a minute. Suppose I'm taking this graph V1 and V2 and I'm connecting the 2 points by 2 edges, E1 and E2, and I'm considering a self loop like this, which is E3. Now see what is happening. If I consider degree of V1 to be 2 and degree of V2 to be 3, then degree of V1 plus degree of V2 gives you 5, which cannot be expressed as the multiple of 2. Okay, so it is not satisfying the theorem. But if the self loop is counted twice, then degree of V1 is equal to 2 and degree of V2 will be equal to 4. Then in this case, degree of V1 plus degree of V2 will give you 6, which is 2 into 3. Now you see, 3 counts your edge. So this is actually satisfying the theorem. And therefore, because of this reason, because these examples will creep in the theory of graph, therefore the mathematical community have come into agreement that they will count the self loop twice. So it is in agreement with the theorem, but this is not in agreement with the theorem. This is not happening, but this is correct. Okay, so after we get this particular, after you get this particular theorem, then another theorem which is there you can see as they have mentioned it as theorem 1.1, which goes like this. Just a minute. So the theorem is the number of vertices of odd degree in a graph is always even. So what they have done over here is simple mathematics they have done. You already know from the previous example that sum of the degrees of all the vertices from 1 to n. See, there are n number of vertices, that is twice the number of edges. Okay. Now you can divide this sum into two parts. One part is this one. This is one part. Why? Because this part contains all those vertices which are having uh, all those vertices which are having even degree. So here J is actually even, and you can divide the rest of the part with those vertices having the odd degree. So this part is summation dvk, k is odd number, and that is actually becoming your twice e. But you know that this number is an even number, and this number is also an even number. Why? Because sum of the even number is always equal to the even number. So you can express dvk odd as the difference of two even numbers. And which becomes even. So sum of this odd number of vertices is also even. So that's why they have got this equation number 1.3. And because in equation 1.3, each dvk is odd, the total number of terms in the sum will also has to be odd. And therefore, the result is proof that the number of odd vertices of odd degree in a graph is always even. Number of vertices of odd degree in a graph is always even. If I again consider our two previous example, first of all, I am considering the example V1 and V2. This was the simple example. And you see that degree of V1 was 1, which is an odd number. Degree of V2 is 1, which is an odd number. But how many vertices are there which are having odd number? 2. So it is, this number is actually even. So how many vertices in this graph are having odd degree? That is 2. So this is in at par with our result. If I consider the second result, V1 and V2 with self loop and parallel edge. So what we get, degree of V1 is equal to how much? 2. And degree of V2 is equal to how much? 1, 2, 3, 4. In this particular case, you are actually having no vertex with odd degree. So we don't have to consider this particular problem at corresponding to the theorem. So this is something which is different from the theorem, because in this particular graph, no odd degrees are present. Okay. So this previous theorem, that was actually not theorem. This is the property of the graph theory, that sum of the degrees of all the vertices is twice the number of edges. Is not a theorem. It is an inherent property of the graph theory. And the theorem that I have mentioned just now, these are the two important aspects which always come into play in different parts of the graph theory. These are these are two basic properties which you need to remember. And after this, they have given you a definition, which is also very important, that a graph in which all vertices are of equal degree is called a regular graph. If you can find a graph where all vertices are of equal degree, say for example, if we draw a triangle where the degree of the vertices v1, v2, v3 respectively are 2, all these vertices are having equal degree, which is true, which is 2, such a graph is actually called the regular graph. So triangle is a kind of regular graph. Okay. So let us proceed. Isolated vertex, pendant vertex, and null graph have already been discussed in the beginning of today's session. So I'm quickly move on to the exercise. In the exercise, you can find various examples, but we will not do all the examples because these examples are mainly, some of the examples are related to games and other things. So all these examples are not important for our purpose. We will try to quickly prove the result mentioned in 1.11 and 1.12. So in 1.11, what is mentioned? Let us try to find out. In 1.11, it is mentioned that if we have a graph, I'm actually considering this one, this property. So if we have a graph capital G, you will try to understand first of all what I'm doing, and later you can reproduce it, you can rewrite it in your copy. Okay, so just do not waste time by writing these things in your copy. Suppose we have a graph capital G. In this particular graph, we have the vertex set V and edge set E. Here E is not equal to 5. Remember. Now, if we consider such a graph, and suppose the vertex set contains n vertices, V1, V2, Vn, it is saying that if I consider any vertex, say V1, let V1 be any vertex. V1 be any vertex. Then, and not only this one another extra condition they have imposed here over here. That condition is this graph is actually a simple graph. So in this particular graph, there is no such, there are no such self loops and parallel edges. Okay. So if I consider any vertex V1, they are saying that degree of this vertex V1 should always be less than or equal to n minus 1. Degree of the vertex V1 should always be equal to less than or equal to n minus 1. So that means the maximum degree of any vertex in a simple graph with n vertices is n minus 1. So we are going to prove this particular result. They have mentioned that they have asked you to convince yourself, means you are to give some mathematical argument to prove this fundamental result. Suppose, if possible, we assume, if I name it equation 1, in equation 1, that 1 is not true. This result is not true. That means what? That means degree of this vertex V1 will be greater than n minus 1. Degree of this vertex will be greater than n minus 1. And if I take, if I want to keep our result general, so for making general argument, we consider this to be the ith vertex. Okay, because I am going to take the summation over all the vertices on both the sides. So let us consider this vertex to be not V1 but I, to generalize the situation. Now I am going to consider the summation of all the degrees of all the vertices on both sides. So on both sides I am going to take the summation like this. So what will I get? On the left hand side I will get twice E, twice the number of edges. On the right hand side we will get n into n minus 1. Okay, and this implies that your E, if E is the number of edges, E is the number of edges, this gives you that E must be greater than n into n minus 1 by 2. So if we assume that sum of the degrees, if we assume that maximum degree of any vertex in a simple graph is not n minus 1, then this has to be true. This has to be true. Now you are trying to find out a counter example to the following result. If I call this result as star, now corresponding to star, if I consider the triangle, the simple graph, which is this triangle. Okay, in this triangle, the number of edges is equal to, sorry, not number of edges, number of vertices is equal to 3. Number of vertices is equal to 3, as we can see. And according to this, if star to be true, this means that number of edges in this particular graph should be greater than 3 into 3 minus 1 by 2. So this implies E should be greater than 3. What does it mean? It means that given 3 vertices, you can draw more than 3 edges to connect them. You can draw more than 3 edges to connect them, where parallel edge, drawing of parallel edge and drawing of self loop are prohibited. Okay. So, and you know that if we consider a simple graph, if it is not a simple graph, then it is all right. But since we are considering the graph to be a simple graph, then this condition is actually impossible. You cannot draw it. So why am I getting these contradictions? It's a kind of contradiction we are getting, that we will not be able to connect these three vertices with edges where a number of edges is more than 3, where the graph is not simple. Why this contradiction is coming? Because I have got star. Why have I got star? Because I assume that this is not true. I assume that this is not true. This is not true, and therefore my assumption is wrong. So by contrapositive argument, we immediately say that degree of any vertex must be less than or equal to n minus 1, and therefore the result is true. So with this mathematical logic, we can quickly prove the given result. And the second one is pretty simple enough. The second proof is pretty simple enough. It is saying that corresponding to the simple graph, that with n vertices, the maximum number of edges must be equal to maximum number of edges must be n into n minus 2. We have already discussed this text section, but yet if I would like to write it once again, I will take the help of this 1.11. So since degree of each vertex is less than n minus 1, less than or equal to n minus 1 from our example 1.11, this implies that summation of over all the degrees should be less than or equal to n into n minus should be less than or equal to n minus 1, and summation over I, and this implies that twice E must be less than or equal to n into n minus 1, and this implies that E must be equal to less than n minus n into n minus 1 by 2, which proves that maximum number of edges in this particular case should be n into n minus 1 by 2. Now you can write in the chat box your roll number. I have activated it. Now to prove this 1.12, you need to take the help of 1.11, and to prove 1.11, you need to take the help of the mathematical logic. Okay, so mathematical logic and group theory are tremendously important to study the graph theory. So therefore, if you have understood the logic behind proving this 1.1, you can reproduce it. If you haven't got my point, then you can revisit my video once it is uploaded in the YouTube, and then you can go through the part once again. Quickly write your roll numbers in the chat box. We shall discuss the rest of the topics in the next session. I have got the attendance of only 11 participants.